Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 2.3 from section 1. So let's get into it. The first part asks us to show that if we have two sets of homogeneous polynomials with one contained within the other, then the smaller one's vanishing set contains the larger ones. So what we should do is fix a point within the vanishing set of the larger one and consider f in T1 arbitrary. As f is in T1, it must be within T2, but as p is within the vanishing set of T2, this then implies that f of p equals 0. Now, as f was arbitrary, we can therefore say that for all f in T1, f of p equals 0. In particular, this means that p is within the vanishing set of T1. Now, the vanishing set of T2, p within the vanishing set of T2 implies that p is within the vanishing set of T1, which is the equivalent statement to what we are trying to prove. So, the vanishing set of T2 is therefore contained within the vanishing set of T1, and we are done. So, we can now move on to part B, which asks us to show that if we have two subsets of p to the m, one containing the other, then the smaller one's ideal is contains the larger ones. So, fix f in the ideal generated by y2 and a family of homogeneous ideals such that fi of p equals 0 for all p in y2 and f equals the sum of fi gi for gi each within S. Consider Q in Y1. Fi of Q equals 0 for all Q in Y1, because Q is therefore within Y2. So, F equals the sum over I and I of Fi gi with Fi of Q equals 0 for all Q in Y1. Fi is within SH and Gi is within S. Therefore, F is within the ideal generated by Y1. Thus, we have shown what we want to show, because f is in the ideal generated by y2 implies it's within the ideal generated by y1. Therefore, I of y2 is a subset of I of y1. And we can move on to our next question, which is to see that for any two subsets of p to the n, the ideal generated by their union is equal to the intersection of their respective ideals. Firstly, y1 union y2 contains y1 and y2 by definition. Therefore, the ideal generated by y1 union y2 is a subset of the ideal generated by y1 and the ideal generated by y2. and the ideal generated by y2. Therefore, the ideal generated by y1 union y2 is a subset of the ideal generated by y1 intersect the ideal generated by y2. Now, it is a fact that for any generating set S and T, the intersection S intersect T is a subset of S union T. We can try this with the even numbers and the multiples of 3, which is a subset of 2, 3 equals Z. And you can try this with any ideals. This always works. This definitely always works in a commutative setting. I'm not sure if it always works in a non-commutative setting, so don't quote me on that. But therefore, we apply this in our favor. So it's a subset of S to the H such that f of p equals 0 for all p in y1 union f in S to the H such that f of p equals 0 for all p in y2, which is equal to the ideal generated by f in S to the H such that f of p equals 0 for all p in y1 or y2, which is, using the conventions here, 1 union y2, which is equal to the ideal generated by y1 union y2 by supposition, by definition. Therefore, the ideal generated by y1 union y2 equals the ideal generated by y1 intersect the ideal generated by y2. So we can move on to 2.3d. So, firstly, we use results which we have already proven by I.2.2 VP of I non-empty implies that the square root of I, or the radical of I, is contained and not equal to S plus. That's one of the things which we proved yesterday. Oh goodness. Now, by I.2.1, the ideal generated by VP of I intersect S plus equals the ideal generated by I intersect, equals the radical of I intersect S plus. That is what we proved, and that is what we stated yesterday as the result of the homogeneous Nullstellensatz. Therefore, as we are working in an ideal entirely contained within S plus, in our context, the radical is equal to the radical intersect S plus. So we have yet to show, we want to show the ideal generated by this, oh goodness, VP of I is contained but not equal to S plus. Now, this is non-empty. So, the ideal of any anything here which isn't empty we want to show is that. So we recall that the ideal generated by some set is equal to the ideal generated by this, where whoop, such that I tilde y equals f homogeneous such that f p equals 0 for all p in y. So, in fact, we don't even need to show that it is not equal to. We can just show that. In fact, all this means is that we want to show that S0 is not a subset of the ideal generated by VPI. But nothing within S0 vanishes anywhere. So this is true. Therefore, this is true. Therefore, I of the vanishing set equals this intersect S plus equals this intersect S plus equals the radical of I. In particular, we skip out these two redundant things. I VP I is equal to the radical of I. So, we continue. We want to now show that the radical of I is equal to the closure. So, what we want to show, well, firstly, suppose there exists T such that the vanishing set of T, the vanishing set of T is equal to that. i.e., it is a i.e. T is a set of homogeneous elements such that the vanishing set of T is a subset of, Y contains within it. Y is contained within it, and it is the smallest with respect to this. Now, in particular, VPIY is contained within VPT. Consider a function within T. We want to therefore show that it is a that it is contained within I of y. As y is contained within the T, f of p equals 0 for all p in y. Therefore, f is within I of y. Is this because f is homogeneous or homogeneous, i.e. it's part of the generating set, so it's contained within. Therefore, T is contained within I of y. Therefore, VPI of y is contained within VP of t by part B. But this would violate the minimality of of the closure. Therefore, is a subset of the closure of Y is a subset of VPI of Y. This is because the vanishing set of I of Y contains Y. Because P in Y, well, is also P in the vanishing set of I of Y. Well, F in I of Y is of the form where Fi of P equals 0. F of P is the sum of 0, which is 0. Therefore, Y is contained within Vp of I of Y. Which is this statement here. And thus we are done. So I will do my customary thank you for watching. Okay, goodbye.